So chemical reactions involve making and breaking covalent bonds. So when a bond is broken, which is what we're going to focus on this video, the electrons have to go somewhere. So there are two choices. Either we take both electrons, so a bond has two electrons in it, we either take both electrons and put them onto the same atom, and this is called heterolytic cleavage, and that's how the HA bond cleaves in an acid in the Bronsted acid-base reaction. Because fundamentally what is an acid is something that loses a proton, the hydrogen gets lost as a proton, and the electrons both go onto element A, whatever that is. And then the other option is each atom gets one electron, and this is called homolytic cleavage. Now I want to pause for a second and just tell you where these terms come from, because people frequently get them backwards. Hetero, of course, means different. And you may be wondering why a cleavage in which we're putting both electrons onto the same atom is called heterolytic. Well, the origin of the term is that the two atoms that used to be participating in the bond are now different in terms of how many electrons they have, in that one of them now has both of the electrons and the other one does not have any electrons. The H doesn't have any electrons and the A gets both of them. Because they're different, it's heterolytic. Whereas when you do homolytic cleavage and put one electron on each of the atoms, the two atoms look the same with respect to the number of electrons that they have. Okay, so I'm going to make you a table now and show you a couple of things that happen as a result of these different types of cleavage. So heterolytic cleavage, as we already saw in the lesson introducing curved arrows, uses what I will call a traditional curved arrow to show the movement of that pair of electrons. And the result of a heterolytic bond cleavage is that you put a positive charge on one atom and a negative charge on the other atom, which means that you are generating a cation and an anion. Okay, so an example of a heterolytic cleavage that we will be seeing a lot of in organic chemistry is the cleavage of a carbon-bromine bond. And in this case, the electrons from the carbon-bromine bond both go on to Br to form bromide, Br minus, and the carbon is left with a positive charge, forming a carbocation. Homolytic cleavage, on the other hand, instead of using traditional curved arrows, they use singly barbed arrows, which are indicated on the example here. In the end, you end up with no charge on either of the two atoms. So in this example, we have a molecule of elemental bromine, Br2, breaking apart, cleaving the bromine-bromine bond to form two Br atoms which have an unpaired electron. They have 7 electrons like a single atom of a halogen would, based on it being in group 7 of the periodic table. Anything with an unpaired electron is called a radical, also known as a free radical. So a molecule of elemental bromine breaks apart to give 2 bromine radicals, which are sometimes called Br dot, because when you have an unpaired electron, it looks like a dot when you're a single dot by itself when you're drawing the Lewis dots. The arrow for this, as you can see, has just one barb. So that's each barb is the arrow's way of indicating a single electron. So normally electrons are going to travel together in pairs, but if they don't travel together in pairs, it's kind of like you take the arrow, split it down the middle for one of the electrons going to the left and one of the electrons going to the right. All reactions in first semester organic are going to involve heterolytic bond cleavage. Homolytic bond cleavage to form radicals is an important class of organic reactions. However, in our course, we delayed discussion of radicals and their reactions until the second semester, after students have completely understood and internalized the ideas associated with ionic mechanisms that involve the transfer of 2 electrons at a time rather than just the movement of 1 electron at a time. Okay, so for the rest of the first semester course, we'll be focused on heterolytic bond cleavage. And an important question that gets generated is, if you're going to put the 2 electrons onto 1 atom, which atom gets the electrons? Okay, when I cleaved the carbon-bromine bond in this example, I just told you that the 2 electrons go on the bromine. But how did I know that? Well, this is a very, very simple rule. Whenever you cleave a bond heterolytically, the electrons go onto the more electronegative element. Because that's what it means to be electronegative. Electronegative elements want to take on electrons more, and less electronegative elements are happier taking on a positive charge, which is what has to happen for this carbon. The example of heterolytic bond cleavage that we saw here is actually closely related to the topic of our next lesson, which is Lewis, as opposed to Bronsted-Lowry, acid-base reactions.